Question 5.3. We are given a reversible reaction, and in the first question we are asked about the energy change during the reverse reaction, whether the net change was a release or an absorption of energy. We are given the heat of reaction, delta H. And remember, when the heat of reaction is written next to a chemical equation, it is referring to the forward reaction. Since the heat of reaction is negative, this means that the energy of the reactants is greater than the energy of the products, and so in the forward reaction, there is a net release of heat energy. So the forward reaction is exothermic. Automatically, this means the reverse reaction must be endothermic or energy absorbing. So energy is absorbed in the reverse reaction. Then we are asked to define an activated complex. An activated complex is a high energy and unstable transition state which forms while the reactants are changing into products. The next question tells us that a catalyst is added to this reaction system, namely vanadium pentoxide, and we need to explain how it speeds up the reaction. Catalysts enable a reaction to occur by a different pathway or mechanism, and this different pathway has a lower activation energy. So, if a reaction has no catalyst present, the activation energy is higher, and with a catalyst, the activation energy is lower. A lower activation energy means more particles possess enough kinetic energy to react when they collide. In other words, more particles have an energy greater or equal to the activation energy of the reaction. And so more particles can undergo effective collisions per unit time. And this means the rate is faster. We are then told that more sulfur dioxide is added to the reaction vessel, and we need to say what happens to the heat of reaction. We need to know that delta H depends only on the energies of the reactants and products, and not on their amounts or concentrations. When more SO2 is added, its concentration and pressure increases. The equilibrium shifts to the right and favors the forward reaction, according to Le Chatelier's principle, and more SO3 is produced. Now, although more heat is released overall because more reaction occurs, the heat released per mole of reaction, which is the value of delta H, remains the same. Delta H would only change if the reactants or products change, or if the temperature changes. So delta H remains the same. Finally, we need to redraw the given Maxwell Boltzmann curve, and we must draw a new one showing how it changes when SO2 is added. We need to know that because the temperature remains constant, the shape of the curve does not change. In other words, the peak does not shift to the right or the left. The peak stays at the same kinetic energy value, and the kinetic energy distribution is unchanged. Although the temperature is not changing, the total number of particles is, because sulfur dioxide is added. And so the area under the curve increases. Because there are more particles at every kinetic energy, the height of the curve increases proportionally. The green curve that we must draw mostly follows the original curve, but sits higher on the y-axis.